All right, welcome. Today we're going to talk about something super practical. How do you take a machine learning model, the one sitting in a developer's notebook, and turn it into a powerhouse service that can handle just about anything you throw at it?
So picture this. It's Black Friday. Your e-commerce site, ShopSmart, is about to get slammed with a massive wave of customers. We're talking a tenfold increase in traffic. And your churn prediction model? It's absolutely critical for sending out those last-minute deals. But the big question is, can it actually handle the heat?
Because a simple model just running on one server, well, it would just fall over instantly, and that could cost millions in lost sales. So, what's the secret? How do you build an ML system that doesn't just survive, but actually thrives under that kind of pressure? Okay, let's get into it.
Okay, so first things first. Our model needs a proper front door. And I'm not talking about some flimsy script. This is the main entrance, the place where the entire world is going to come knocking for a prediction. It has to be, well, bulletproof.
And for that front door, we're going with Fast API. And listen, there's a really good reason for this. It's designed for high performance, which is exactly what we need for a great user experience. Plus, it uses standard Python type hits to build a really rigid structure. It's not just fast, it's also self-documenting and way less prone to bugs. A real win-win.
Now, what really makes this thing ready for the big leagues are these three features. The health check is crucial. It's how our management system knows if the app is alive and well. The metrics endpoint gives us a window into performance, feeding data to our monitoring system. And this last one, Pydantic validation, think of it as our bouncer at the front door. It automatically rejects any garbage requests before they even get close to our model.
So, we've got this great API. Awesome. But now, how do we make sure it runs the exact same way on my laptop as it does in a massive cloud environment? We need a kind of universal recipe for it.
Yeah, this. But it works on my machine. We've all heard it, right? It's the classic engineering headache we're trying to get rid of. Inconsistencies between environments just lead to disaster. The solution? It's all about containerization.
So we turn to Docker. What Docker does is, it basically shrink wraps our entire application, the Fast API code, the model itself, all the libraries it needs, into one neat little package. It's like a universal shipping container for our code, which means it's guaranteed to work the same no matter where you run it.
And the Docker file? That's our recipe card. See here? We start with a clean Python base. Then we pull in just the libraries we need, copy our code, and tell it exactly how to start up. Every step is precise. This isn't just nice to have. This kind of repeatability is absolutely crucial for any kind of automated deployment. Okay, so now we have this perfect portable container. Great, but one container isn't going to cut it during that Black Friday madness. We need someone to conduct the whole orchestra of containers. We need an orchestrator.
And this slide, right here, shows you exactly why we go with something like Azure Kubernetes Service, or AKS. A traditional virtual machine, it's fragile. It's a single point of failure. You have to manually scale it. But AKS, it's a whole different ballgame. It scales automatically. It heals itself if something breaks. And, this is huge, we can update our model with zero downtime for our users.
Right, so we've got our conductor, Kubernetes, but how do we actually tell it what to play? Well, we don't just shout at it, we give it a set of detailed blueprints, or as they're called in the Kubernetes world, manifests. First up is our deployment.yaml. This is where we tell Kubernetes what we want our application to look like. We're basically saying, hey, take my churn API container, and I want you to make sure there are always 2 copies of it running. And these copies, by the way, are called pods. Now, here's the cool part. If one of those pods gets sick and fails its health check, Kubernetes just gets rid of it and spins up a fresh one, instantly. That is self-healing. Okay, next up, the service.yaml. So remember how those pods can come and go? Their internal addresses are always changing. That's a problem, right? Well, this service manifest solves that. It creates one single, stable, public IP address and a load balancer that's smart enough to send traffic only to the healthy pods. This becomes the permanent public front door to our entire system.
And now for the real secret sauce. This is how we handle that Black Friday traffic spike. The HPA YAML, or Horizontal Pod Autoscaler. This thing is amazing. It tells Kubernetes to just watch. Watch the CPU usage on all our pods. The second that average usage creeps above 80%, bam! It starts launching new pods, scaling us up to a maximum of 10. And then, when the rush is over, it scales us right back down to 2, which saves us a ton of money.
So, let's step back for a second. We've built the app,
We've packaged it up, we've given our orchestrator the blueprints. What's the payoff here? What does all this smart engineering actually mean for the business?
First off, pure speed. We're getting predictions back in under 50 milliseconds. That's way faster than our 100 millisecond goal. What this means is, for the user, the experience is instant. There's no lag, no waiting, it just works. And second, and this is a big one, look at the cost. This chart shows the real beauty of autoscaling. Our normal day-to-day cost with 2 pods running is pretty low, right? Around $200. Then Black Friday hits. We scale up to 10 pods, and yeah, the cost goes up. But, and this is the key, as soon as the traffic dies down, the cost drops right back down. We are only ever paying for the horsepower we are actually using.
So when you put it all together, what do you have? You have a system that is scalable, so it can handle huge events like Black Friday without breaking a sweat. It's highly available, basically always on, thanks to that self-healing. We can roll out new model versions with zero downtime. And it's incredibly cost-efficient. We've built something that doesn't just work, it actively protects revenue and makes customers happy.
So look, we've totally nailed the engineering side of this. We've built a scalable, reliable system. But in the world of machine learning, there's another, sneakier problem. The world itself doesn't stand still. Customer behavior changes, trends shift, and that can make even the most perfectly built model go stale. How do you deal with that? Well, that's a story for another time.